It's okay, Pierre.
Hello, Giovanni. You hear us?
Yep, it's fine. Yeah. Hello.
Hello. How are you?
Good, thank you.
Yeah. So I'll let you present Matilde and present the speakers. I'm gonna recall while I recall everybody. Okay.
Yeah. Can you introduce the next presentation, please?
Yes. Can we start already directly? Okay. So our next speaker is Matilde Marcolli from the University of California, and the talk will be about topological neural-information networks.
Thank you very much. I will ask you to turn off your micro and your camera when we are presenting with the others.
My goal is to talk about some recent work and collaboration with Yuri Manin, which is in this paper, some in the archive, and is part of a longer-term project which involves also collaboration with neuroscientists. So the main goal is to try to understand how one can use pharmacotheoretic methods to model neural networks with associated resources, especially informational resources. So I'm going to go through quickly the main motivations for this work. And one of them is the fact that in various simulations of activity of the neural cortex, as well as in experimental observations of neural responses, one often sees a peak in non-trivial homology and persistent homology. And in the parts of the network that is corresponding stimuli. And it is generally believed that there is a functional interpretation for this non-trivial homology, and that somehow this is necessary for processing stimuli. And one of the questions is, in that sense, what is the role of this non-trivial homology? And a related idea that actually arises from the theory of concurrent and distributed computing is that often, when one models certain processes of concurrent and distributed computing through algorithms, this can be modeled by certain simplicial complexes and operations, and these simplicial complexes that describe the way that various parts of the process share resources. And it's known that there is indeed a functional role for non-trivial homology, and that certain processes can complete their task only if there is enough non-trivial homology in the corresponding complexes. So, in a sense, this suggests a related possible illustrative application for what this non-trivial homology is doing, that it is allowing certain kind of distributed processing to complete that task. And there is another aspect of homotopy-theoretic structures in neuroscience, which is the way that the geometry of the stimulus space is encoded in the neural code. And various results from that, assuming certain kind of complexity assumptions on the response fields, the homotopy type of the stimulus space is encoded in the complex associated to another problem of the design of which signal fields are activated at the same time. And so in this sense, it seems like the representations that happen to the neural code are encoded in homotopy types. This is essentially a different role of topology or non-trivial topology than the previous one. And in some sense, we see some framework in which both these different currencies of topology arise naturally. And another motivation is the fact that neural network in the brain and the physical brain come endowed with certain various kinds of resources, both in the sense of codes and the associated information measures, but also in the sense of metabolic resources and certain kind of optimization of information transmissions. And so we would like to have a formalism that naturally describes network with associated resources, and where all these different layers of structure are kept. We can keep track of all these different layers of structures simultaneously. And there's a framework that's suitable for that, which is a general mathematical theory of resources based on the language of category theory. And one more motivation is the idea of how to encode notions of informational complexity of networks in the brain. And one of the proposals in particular is integrated information, which is designed to measure the information content of a system that cannot be broken down into its component subsystems. And there's a kind of somewhat controversial proposal around this notion of integrated information that we should provide a quantitative measurement of consciousness. And it seems more expected that a sufficiently high level of integrated information would be necessary for something like consciousness rather than sufficient. That's still what one would like to see is a formalism, kind of topological formulation of how representations are constructed by methods of codes and the brain. That will, as a byproduct, give rise to enough integrated information. And so the main idea for all this is to develop a homotopy theoretic modeling of neural information network. And so what we learn from this is a basic parts of the structure are a topological space that describes all the consistent ways. So it's like a configuration space in a physical sense. So it describes all the possible consistent ways of assigning to a certain population of neurons, with a network structure, some computational resources, some kind of concurrent distributed computational architectures, and associated resources of information, conversion of resources, and transmission of information. And we want this description to also keep track of homotopy types that occur so have a way of getting associated invariants like homotopy and homology invariants. And so, as I already suggested, there's a natural language for these things in the setting of category theory, which is especially suitable because the category theory both conveys the idea of consistency of your subsystems and also constraint of resources. So the basic idea about the mathematical theory of resources is that resources are more symmetric numerical categories, so you can combine independent resources and also the resources of independent subsystems. And morphisms in this category represent the convertibility of resources. So not all resources are virtually convertible, but whenever you have convertibility, you have morphism in one direction. In a similar way, one can quantify the convertibility of resources to an associated semi-group, which is based on the isomorphism classes of objects and the operational combination of resources. And this is going to discuss things like maximal conversion rate of resources and so on. And for us, this will be useful when introducing kind of threshold dynamics in this categorical sense. And another part of the picture, the categorical formalism that we want to use, is given by some factors. So if you have a category with a minimal mental structure, namely a categorical sum of the product and the zero object, and one can consider all factors from pointed finite sets or subsets of a given finite set to this category that combine over independence or combine arbitrarily over independent subsystems. So these are all the ways of assigning resources to subsets of a given set in a way that's consistent with addition over independent subset. And one of the ways that this kind of structure is already well known in combinatorial is to see those notional gamma spaces, namely the category of some factors, the simplicial nerve of the category of some factors determines a simplicial set. And this altogether gives a factor from the category of finite quantum sets to the category of quantum simplicial sets. And that is, so this is topological space, as we say, is our configuration space of assignments of resources to subsystems. So the one thing that's good about this construction topologically is that it's known that these homotopy types are sufficiently sophisticated that they're actually able to construct any connected spectra in the sense of homotopy theory. So this means that they are very general and very non-trivial topologically. But also for us, this would be like a configuration space. So there are assignments of resources of this type C to subsystems of this system X. Of course, at this point, this is rather coarse because subsystems here just mean subsets of a given finite set. And one can add more structure because we really want networks, so sets that have a structure of directed networks. But a directed graph itself has a categorical interpretation as a functors from a category to edges and vertices to another category of finite sets. And one can use this formulation to adapt this gamma spaces formalism to the case where sets are related by these source and target maps of directed graphs. So we have a set of edges, not just one set, but we have a set of edges and a set of vertices related by source and target maps. And so, for example, you can say how these assignments of resources should be compatible with this source and target map that describe the network structures. And for example, you can have assignments of resources to the incoming edges and the outgoing edges at a given vertex, and resources assigned to the vertices themselves. And there are nice categorical ways to describe constraints that one can put. For example, the equalizer of these functors determined by the source and target maps of edges, the edges, vertices, is a way to describe them. You expect the resources to have conservation laws of vertices, so the amount of resources that are flowing in along the incoming edges should be equal to the amount of resources that are flowing out from the outgoing edges. And there are other kinds of conservation laws that can be formulated that are more sophisticated than just these conservation laws like practices and can be expressed in terms of other more general inclusion and exclusion relations or subnetworks. But we're just focusing this case here for simplicity. And so, what kind of resources we want to consider? For example, we know that there are neural codes associated with networks, so we can formulate, translate the usual formulation of what the neural code is. So, the subset of the population of neurons that are firing at a given time, what type of window of time divided into subintervals with which observations are made. And we can form a category of codes that reflect this structure. And possibly with other weights to these codes. And so I'm not looking into details, but the point is that, for example, you can recover from this as a fractional conservation of practices and this this category of weighted codes. A simple categorical version of the linear model of the neuron where you have most networks that you have a single output and a number of incoming inputs. But you can do something better, which is like giving a categorical version of certain dynamical systems, like a typical field dynamics of networks. And for that, it's convenient to think in terms of a finite difference version of the usual threshold of dynamics, where one has certain weights and a certain thresholds or parts of threshold function. And the way one introduces a threshold in this categorical sense is exactly in terms of this measuring the convertibility of resources. When you have, as long as you have convertibility, you're above the threshold, and you don't get cut off by the threshold. And the variables that enter in the equations are in the functors of this category of resources. So more precisely, you have a category of some functors with invertible transformation and with conservation of vertices in various equalizer conditions. And the initial condition, which is itself one of the summing functors. So the initial condition is an assignment of resources to your network, and this assignment of resources is dynamical and it evolves according to an equation which mimics the usual field equation in terms of the name of functor of the category of resources and the threshold which is given by this convertibility of property of resources. The dynamics have various properties. For example, this is dynamics in a category. So one can try to formulate certain properties of every this categorical level, like existence of fixed points and so on. And but one things that it induces the discrete topological dynamical system on the nerve, on the realization of the nerve of this category. And so one can also study this usual dynamical system in this topological sense. And so there's quite a lot of interesting questions that I don't know how to answer at this stage about this kind of categorical formulation of dynamics and the existence of solution and their behavior. In particular, one can formulate this in certain where your category of resources is some kind of category of computational architectures, and there's some nice ways of formulating in terms of the language of automata, the concurrent resources for concurrent and distributed processing. Some speak on some of the details, but the point is that you can construct these nice neural networks because you have a grasping operation, so you're sourcing with inputs and outputs. And so if you have like the resources assigned to a part of the network, you can grasp them to inputs and outputs of that part. And this have also specific descriptions in terms of the structure of the network, like it's just connected components, it's conversation graph, with some how these connected components are related to one another. And among the applications of this computer, you can think of your automata and model discretize individual neurons and the way that these are wired. And you can also adapt this to model some kind of non-local neuromodulation effects. And finally, I will just say a word about integrated information. So a way to formulate that is in terms of the types of information that's not independently recovered by splitting the system into independent subsystems. And there's a way to formulate that. There's a minimization problem of Hilbert-Leibler divergence and in terms of geometry information, which I won't go into. But the point is that there is also a way to give it a chronological interpretation along the line of the work of depending on what their own signal. And this one can integrate with this point of view on homotopy types. So I just want to end here as we've stopped my time. The point is that this construction of homotopy type, inside this construction of homotopy type, one can recover what the homotopy types associated to neural codes. One can also encode homotopy types that are coming from computational system about distributed computing. And one can recover synthetic sets coming from complexes of activated subparts of the network. So these various different layers of topology, they all occur at the same time in this framework. And one can also see that the simultaneous and integrated information follows from this structure. Okay, I will end this talk here. Thanks for your attention.
Yeah, it's very good. Do we have any questions for our speaker that I see is in the?
Just one question.
I erroneously said, I mean, of course, I meant Caltech when I was introducing you. Sorry.
So basically, could you make what would represent in terms of neural assemblies the homotopy type of in neural networks? Because there are some theory of synchrotron chains, and for instance, which intuitively should be related to the propagation of the information flow within the neural networks. Do you think it could be related?
Yes, yeah, definitely. So that's something that I'm actually thinking about how to incorporate that kind of information into this picture. Yeah, I mean it's not yet at this point part of the picture, but it's definitely something that looks like it should be incorporated into this model. Yes.
Thank you.
Thank you very much.
Yeah, I know there's no time for questions, but if anybody has questions, please just feel free to send them to me and I'll get back to you.